All right, let's dive right into this explainer. Today, we're going to demystify the ultimate mathematical tool used to prove exactly how two things are connected. I mean, if you've ever wondered how we can confidently state that smoking causes health issues or how height relates to weight, well, you are looking at the invisible machinery of the Pearson correlation coefficient. It's the silent engine driving so much of our modern scientific understanding, and by the end of this, we're going to have it totally mastered.
We've got a super clear roadmap for today. We're going to hit measuring mathematical relationships, the -1 to 1 scale, the geometric angle, sensitivity and blind spots, and finally, variations on a theme. So let's kick things off with Section 1, measuring mathematical relationships.
Here is the foundational problem, right? How do we mathematically prove two things are linearly connected? It's the classic apples and oranges dilemma. If we want to look at, say, the age and height of a sample of school kids, we run into an immediate roadblock because we're dealing with entirely different units. How do you mathematically compare years of age with inches of height? We really need a robust way to completely strip away those units so we can see the underlying pure mathematical relationship underneath. And that is exactly where Pearson's R swoops in to save the day. It elegantly solves our apples and oranges problem by taking the covariance, which honestly is just a simple measure of how much two variables vary together, and dividing it by the product of their individual standard deviations. The equation effectively cancels out the units. It's like magic. What we're left with is this pure, unitless measure of linear correlation. It lets us directly compare how one thing changes in relation to another without getting bogged down by the raw, messy measurements. But before we get into how to actually read this number, let's trace this back through history, because it's a pretty fascinating timeline. Auguste Bravais actually derived the core mathematical formula way back in 1844. Then, decades later in the 1880s, Francis Galton introduced related ideas about reversion and regression. And Carl Pearson, well, he just took those concepts, formalized them, and basically brought the whole thing to the finish line later on. Which brings us to a frankly hilarious real-world example of Stigler's law of eponymy. Now, if you don't know it, Stigler's law states that no scientific discovery is ever named after its original discoverer. Considering Carl Pearson gets all the historical credit and literally the namesake for a formula he didn't even initially derive, I'd say Stigler's law is performing with absolute perfect correlation here. All right, moving on to Section 2, the -1 to 1 scale. Once those units are stripped away, Pearson's R always gives us a number constrained within a very specific, elegant mathematical boundary. That boundary tops out at a +1. Now, a correlation of exactly 1 represents an unrealistically perfect positive linear relationship. Imagine a scatter plot where every single data point forms a flawless, ascending straight line. As one variable goes up, the other follows precisely in lockstep. To be honest, you will almost never see a perfect one in messy real-world data unless you're in a highly controlled physics lab. Right dead in the middle of our scale, we have 0. A 0 means there is absolutely no linear dependency between the two variables you're looking at. If you plotted them out, it would literally just look like a random cloud of dots. Mathematically, we say they are completely orthogonal or uncorrelated. Knowing the value of one variable gives you absolutely 0 predictive power over the other one. And way down at the bottom of the scale, -1 indicates perfect anti-correlation. Now, it is absolutely crucial to understand that this isn't a lack of correlation like a 0. No, it's a perfect inverse relationship. As one value increases, the other decreases in a perfect straight line descent. It is just as strong of a predictive relationship as a positive one. It's just pointing in the exact opposite direction. Let's look at a specific 5-country example from our source material to put this into perspective. We have GDP figures of $1, $2, $3, $5, and $8 billion, and those are mapped directly against poverty rates of 11%, 12%, 13%, 15%, and 18%. If you plot this specific GDP and poverty data, it perfectly follows a strict linear equation, y equals 0.10 plus 0.01x. Because every single data point sits exactly on that line, calculating Pearson's R for this exact set results in a perfect positive correlation of exactly 1. Let's pop open the hood in Section 3, the geometric angle. We're going to translate this algebra into simple geometry to see how it actually works visually.
If we take our data, center it so the average is 0, and treat the numbers as vectors pointing outward in space, the Pearson correlation coefficient is literally just the cosine of the angle between those two vectors. Just pause and let that sink in for a second. If the angle between the vectors is near 0, they're pointing in almost the exact same direction. The cosine of 0 is 1, which means high correlation. But if the vectors are at a right angle, 90 degrees, the cosine is 0, meaning they're completely orthogonal and there is 0 correlation. It's such a brilliant geometric translation of raw data.
And this perfectly illustrates why context matters so deeply when you're reading these geometric angles. An 8-point correlation might be considered a complete failure if you're verifying a strict physical law with highly precise instruments. But that exact same 8, that is a massive, celebrated success in the messy, unpredictable world of the social sciences. The number itself is absolute, sure, but the interpretation is totally relative. Numbers don't just exist in a vacuum, you know? Human context defines their success.
That brings us to Section 4, sensitivity and blind spots.
Look, every statistical hero has a weakness, and it is absolutely vital to know where Pearson's formula is totally blind. First up, it only measures linear relationships. If your data forms a perfect U-shape, like a parabola, Pearson might just give you a 0, completely ignoring that obvious geometric relationship simply because it isn't a straight line. Second, it's not what statisticians call a robust statistic. A single, massive, extreme outlier can completely ruin your results and skew the angle. Third, if a variable never changes, meaning it has 0 variance, the formula just breaks. It's undefined. And finally, in heavy, noisy data conditions, it suffers from regression dilution, where the true correlation just gets watered down by all the noise.
And that leads us to our final part, Section 5, variations on a theme.
To account for those exact blind spots we just talked about, statisticians over the last century have built this entire extended universe of variations around Pearson's original concept. The most famous offspring is the coefficient of determination, which you probably know as R². You literally just square the sample correlation coefficient. What makes this so incredibly powerful is that it practically tells you what exact percentage of a result is directly explained by your initial variable. If your R² is 0.5, it means 50% of the variation in one variable is explained by the other. It's an amazingly tangible way to measure effect size. And there are so many more variations tailored to specific problems. Got a small sample size? You use adjusted correlation to fix the built-in bias. Are some observations way more important than others? Throw in weighted correlation. Need to filter fast time series data? Scaled correlation is for sure your best friend. What if you're a meteorologist measuring the angle of the wind on a 360-degree compass? You'd use circular correlation. Or, if you want to see the relationship between two things while ignoring a pesky overlapping third variable, you smoothly pivot to partial correlation. But through all of these variations, the core engine, that pure mathematical angle, remains exactly the same. So here's the crucial question I want to leave you with today. We use the Pearson correlation coefficient to define truth in medicine, economics, and science. But if correlation simply measures a mathematical angle between vectors in data space, how much of what we call truth is really just a reflection of the geometric lens we choose to look through? As you look at the data driving our world, just remember, you are looking at a carefully constructed mathematical angle, not necessarily an absolute law of nature. Keep questioning the angles and keep exploring.